Hello and welcome to the Daily Space. I am your host, Dr. Pamela Gay,
And I am your host, Beth Johnson.
and we are here to put science in your brain. Well, we love to tell you what we know. Let's face it, sometimes it's much more interesting to work through a whodunit mystery involving other galaxies than to try and make sense of any more terrestrial mysteries. In our first story of the day, we have the mystery of weird chemical ratios in a dwarf galaxy 430 million light years away in the direction of the Hercules constellation. This little system is a leftover bit from the early universe that, like a bit of unmixed splattered recipe, doesn't contain all the ingredients. And even the existing ingredients, they aren't mixed as expected. This particular system is mostly made of the base elements of the universe, hydrogen and helium. And it is enhanced with a touch of oxygen that was created in massive stars. Surprisingly, these systems also have an unexpectedly large dash of iron. Normally, we expect to see iron to oxygen ratios that reflect the kinds of stars that create these elements under normal conditions. Iron comes from long lived stars that explode as supernovae, and oxygen comes from smaller stars that exhale their materials into the space around them. The rarity of supernova leads to typically less iron than oxygen. But that's not what we see in this weird galaxy. And this is the second weird galaxy like this we've found. To explain these two galaxies, astronomers considered this difference between stars made today and stars made early in the universe and found that massive stars made prior to the creation of heavy elements could have formed both iron and oxygen, creating the chemical recipe we see in these systems. Because these galaxies are small, once those massive stars formed, nothing was really left to make more massive stars. If this theory is true, these systems should contain intermediate sized black holes 100 times the mass of the sun or so. It's unclear how we might observe such black holes in these distant galaxies. But it's still cool that we have a theory for what happened that has an observational test. And maybe someday we'll find a way to see the effects of those possible black holes.
Trying to figure out how to observe things takes up a shocking amount of time. Sure, you can go out, look up, do some science, especially variable star science, with your eyeballs. But it turns out that for every easy thing to observe, there are a dozen things trying not to be observed. Things like neutrinos. These antisocial particles are generated in a lot of different nuclear processes, ranging from fission to fusion to everyday radioactive decay and high-speed collisions. These particles generally pass through us by the thousands without anything happening, but occasionally a neutrino with just the right energy on just the right path can collide with a particle in water and give off a flash of light. Our human bodies are far too small for this to be a concern, but scientists can leverage giant regions of water or ice to look for these flashes. And right now, there are new detectors being built by stringing sensors in grids in the Mediterranean, in Russia's Lake Baikal, and off the western coast of Canada. This global network of detectors, we're hoping that it will become possible using those to figure out what kinds of phenomena are producing the neutrinos. Currently, a massive detector named IceCube is looking for flashes in Antarctic ice. Two of these neutrinos are traced back to events associated with supermassive black holes in galaxy cores. Since we thought these neutrinos came from star-forming regions and supernovae, these discoveries highlight the need for more information. And now, thanks to the Earth having so much water, and the ability of scientists to string sensors together and dangle them in that water, the detailed information we want should be coming.
Finding neutrinos is hard, and not all neutrinos are identical. We know there are neutrinos related to reactions with electrons, muons, and tau particles. And each of these sibling neutrinos has their own mass and their own slightly different way of being found. These three flavors of neutrino are all part of the standard model of particle physics, and they have been observed. And they have been observed to oscillate from one kind to another as neutrinos exchange their mass for energy or their energy for mass. In addition to these known particles, there may also be what are called sterile neutrinos or inert neutrinos that come in a wide range of masses that are waiting to be observed. As the theory goes, the known neutrinos have a particle spin that is called left-handed. Basically, if your thumb is the direction of motion, the property called helicities, which is like the spin but not quite the same, is aligned with your fingers curved in the direction of motion. There is no reason, however, that the other orientation shouldn't exist. That particles shouldn't act like if your right thumb is the velocity and your fingers are the helicities. This "why aren't they also flipped?" question has led to the idea, to the hope, that these alternate neutrinos, these sterile neutrinos, could be out there, refusing to interact with anything other than gravity, and having masses anywhere from 1 electron volt to 10 to the 15 giga electrovolts, which is huge for a particle. And there could be many kinds of them out there with many different masses that together add up to explain dark matter. Trying to discover particles that don't want to interact except via gravity, however, is a challenge. Luckily, the Katrine experiment shown here has accepted this challenge, and in a new paper in Physical Review Letters, they describe how they are looking for sterile neutrinos alongside known neutrinos. Basically, in heavy water, protons will periodically be converted into neutrons. And in the process, they give off 1 electron, 1 neutrino, and energy. The energy, well, the entire system has a decay energy of 18.6 kiloelectron volts that can be spread between the motions of these particles. And the neutrino's energy can get measured as the flash is created when it hits something. And thanks to probabilities, we'll see a range of energies in those flashes that reflect how often those neutrinos get how much of those 18.6 kiloelectron volts. If sterile neutrinos are formed, we should see a different family of flashes that reflect the energy of the sterile neutrinos. So far, the Katrine experiment has been able to rule out masses between 3 and 30 electron volts for sterile neutrinos. If sterile neutrinos are out there, they're probably kind of big. And this is what we need to explain dark matter. The idea that dark matter is just a flipped version of something we already know about is one that really appeals to me. It doesn't wreck the standard model, but expands it in a sensible direction. Hopefully, Katrine will stop ruling out masses for sterile neutrinos and start finding sterile neutrinos. For now, though, we wait and we wonder, what is dark matter and what particles are out there outside the incomplete standard model waiting to be found? After the break, we'll be back to talk about how black holes are also being used to hunt for possible dark matter. Stay tuned. We say the standard model is incomplete because we know the universe's mass energy allotment consists of mostly dark energy, then a lot of dark matter that gravitationally throws its mass around while refusing to be seen. And finally, there's a tiny amount of regular matter, like we're made of. The standard model of particle physics does a good job explaining all that visible, detectable stuff we call baryonic matter. But it offers no solutions for dark matter. The standard model is also based on observations and realizing that if we see X and Y, there is probably also a Z. But it doesn't give us solid physics to explain why there's an X and a Y and a Z needed in the first place, as we've said before. This is like the point when Kepler could explain planetary positions with his 3 laws of orbital motion, but he didn't have gravity to explain why the equations worked. The theory was good. It was just missing the underlying physics. Particle physics is currently at that stage. The standard model is good, but we know it is missing things. Dark matter. 27% of the makeup of the universe. It's a missing thing. And because dark matter only interacts with gravity or when it randomly collides with something else, scientists are looking at every collision and every gravity field for signs of dark matter. In addition to thinking dark matter could be sterile neutrinos, particle physicists think a hypothetical particle called an ultralight boson is also a possibility. In general, bosons are particles that carry force or other properties. The Higgs boson carries mass, the photon carries the electromagnetic force, gluons and WZ particles, they carry the strong and weak forces. It's unclear what ultralight bosons might do, but if they are out there, they should be interacting. One possible kind of ultralight boson is the axion, and if it is out there, it could be interacting with spinning black holes. As the theory goes, a supermassive black hole should pull in clouds of ultralight bosons because let's face it, black holes will pull in anything that gets too close. Since the bosons don't have the same motion as the spinning black hole, when their slow motion selves get pulled in, the black hole should slow down. This is like what happens when someone hops onto a spinning playground carousel. Its rotation spins as it gains its rotation actually slows as it gains their not moving fast enough mass. In looking at supermassive black holes, scientists have realized that fast rotating systems put limits on what mass the theoretical ultralight bosons might have. If we find fast spinning old black holes, that means there probably aren't a large mass of ultralight bosons out there slowing things down as they hop on and hop off the spinning black hole like kids on a carousel. And looking at the black holes, GW 190412 and GW 190517, scientists have determined these 2 old supermassive black holes are rotating pretty much as fast as a supermassive black hole can rotate, which is twice as fast as would be expected if ultralight bosons exist. This means that ultralight bosons, if they are out there, aren't the ultralight masses we imagined. They could exist, just at an even smaller mass than imagined, but the more we look, the more we aren't finding things, and it is starting to get kind of annoying. But this is why we scientists do science. We want to figure out these problems with the universe, and some problems are just going to take a while to sort. After the break, we'll be back to talk bright glows in the night sky. Stay tuned.
Now, let's solve a terrestrial mystery after all. Aurora are nothing new. We've talked about them before, whether it was citizen scientists helping understand the Steve phenomenon or aurora on other planets like Jupiter and Saturn. We are all fascinated by their beauty. And yet, there are still unexplained phenomena when it comes to aurora. Today, however, there is one fewer mystery. Allow me to introduce you to the space hurricane. Let's start with the basics. Aurora occur when charged particles, electrons generally, interact with atoms high in the Earth's atmosphere. The electrons change the state of the atoms, increasing their energy, but that isn't a stable state. The atoms then lose that energy and return to their original stable state, and the energy is released as photons of light, creating the gorgeous colors we see in the sky. So where do the charged particles come from? The sun. In particular, they are carried on the solar wind. And when the sun is in its more active phases, we frequently get aurora alerts. Anytime there is a coronal mass ejection, we can definitely expect aurora in the highest latitudes around the polar regions. If an ejection is particularly large, the aurora can extend into the mid latitudes. I know my family in Minnesota has been able to see them. However, aurorae don't just happen when the sun is energetic. There have been numerous instances of spectacular aurora occurring when the sun is quiet and there is little solar wind. So a research team combed through thousands of aurora images to understand why these events occurred. They found several dozen instances, and one event in particular lasted for 8 hours, giving the team a lot of data to work with. And what they found was that these aurora were spiral shaped and circular, like a hurricane. That 8-hour hurricane occurred on August 20th, 2014, and it was made of spiral arms of plasma that were over 965 kilometers long, spinning around a calm center. Instead of water falling, these atmospheric storms rained electrons over the magnetic North Pole. Now, unlike their more terrestrial counterparts, these space hurricanes aren't a large risk to humans on the surface, but they are important to understand because all that energy can cause fluctuations in radio waves that pass through the ionosphere. That could affect our satellite communication and maybe even navigation. Let's not have ships get stuck because of this. Plus, these storms might heat up the upper atmosphere, which would expand as a result, changing in density. And all of that becomes an issue for the satellites and space debris that orbit at that elevation. Change the drag on a craft and you change its velocity. That makes orbital predictions more difficult. As co-author Larry Lyons notes, if you want to know where the space station is going to be a few hours from now, you have to know what kind of atmosphere it's going through. There are still a lot of open questions about these newly discovered space hurricanes, and lead author Qinghei Zhang lays them out. What controls the rotation of space hurricanes? Are these space storms seasonal like their tropical counterparts, perhaps limited to the summer when the Earth's magnetic dipole is tilted just the right way? And can space hurricanes be forecasted like weather events on Earth? Pamela and I are both excited to see where this new avenue of research goes. The aurora are just cool. We'll be right back after one last break to share some of our favorite science apparel and places to buy them. Stay tuned.
Hello and welcome back. We are working to start bringing you our honest reviews of products related to science, space, and just sometimes waving your nerd flag. And today we're going to take on apparel. Now, if we don't like something, we will tell you. But the truth is, the things we have to share today, we absolutely love and are likely to walk up to people and go, see this, get this, be a nerd with me. And Beth actually did that to me yesterday over Discord as she shared the shoes she got that she's reviewing.
Okay, so these shoes are so cute. All right, what happened was, really quick intro here. We were out. I saw a woman with these adorable shoes. I complimented her on her shoes. This is always a good thing to do with women, compliment what they picked out to wear, and asked her where she got them. She explained. I went to go hunt them down, and in hunting them down, they are made by a company called Hot Chocolate. And my husband and I found the cutest design, and I was sort of, all right, shoes, I'll get them later. But my husband does not feel that way about things when I get kind of giggly about them. So these magically appeared just the other day. So you can see that these have, I mean, look, it says nerdy on it in chemicals. There's E equals MC squared. It's all science. So there's math, there's biology. They're adorable. Look at that. I mean, who wants some organic chemistry on their shoes? And they're rubber soled, very flexible. And I wore them yesterday My feet are not used to this type of shoe anymore, but they were really comfortable. They didn't rub in weird places. They fit nicely. They don't have half sizes, so I will warn you of that. But if you and I put the packaging that came with it away, unfortunately. But they came in a box that looks like a chocolate milk carton. So, do the brains provide good support for plantar fasciitis? No. Well, I have had plantar fasciitis, and I'm going to say that, yeah, they could. These are pretty squishy and supportive on the inside. I really liked them. I didn't have any points of pain in my feet when I wore them yesterday, and I walked around a very large, big box hardware store. I'll let you figure out which one. The logo is orange. So I'm going to say that definitely 5 out of 5 on these shoes. These are adorable and cute, and they have lots of other patterns. These were just the really geeky ones, but if you prefer like a floral or a goth, they had all kinds. So I'm very pleased with this purchase and would highly recommend it. Again, this year these are from Hot Chocolate, and you can find these on Amazon. Pamela, what have you got?
So my story starts very similar. A number of years ago, I saw Bethany Berkshire in a lovely dress that had circuit board pattern in that 1980s green screen color all over it. And I kind of walked up to her and I was like, that dress is amazing. And her first response was, it has pockets. So, folks, if you're ever asked, what do women want? The only answer is pockets.
Pockets.
And then she went on to explain that the dress came in sizes extra small to 5XL, which means there's very few body types on the extremes that these dresses don't fit. And in the years since then, Svaha has continued to expand their line. And they recently came out with a dress that has the Mars Perseverance rover's parachute pattern as the skirt. Now, in reviewing a number of these different dresses in different sizes, not sizes, in different styles, by which I mean by purchasing with my own money a number of these dresses, I am happy to say that while not all dresses fit all body types, they have nerdy apparel that fits all body types. And one of the things they do that allows them to keep their materials in the often under $100 range, which for high-end nerdy clothing is still fairly cheap. They have all of their dresses in just a small number of cuts. So once you figure out what cut of dress fits your body, you can then go off and buy it in programming code, solar system design, dinosaurs, circuit boards, the electromagnetic spectrum, and a variety of constantly changing patterns. They also have dresses that have glow-in-the-dark things on them, which I will warn you, your laundry basket might scare you in the middle of the night should you purchase some of these. This is a drawback to be aware of. But overall, if you're looking for super comfy, super nerdy clothing that fits all sizes and now comes in children's, and there are t-shirts and hoodies for men as well, Svaha USA. And I think that's the end of our review for today.
This has been the Daily Space.